Let's take a look at this physical sciences energy and chemical change test. The multiple choice questions go from 1.1, which reads, consider the energy profile graph for a reversible reaction shown below. Which statement is or are correct? Option 1, P represents the activation energy for the forward reaction. P does not represent the activation energy. P actually represents the energy of the activated complex. Okay, so let's look at our options. A says all are correct, so that's immediately out. Let's look at point 2. 2 says delta H for the forward reaction is equal to R minus Q. Remember, we can calculate delta H by subtracting the energy of the energy of products minus energy of reactants. The energy of my products is R, the energy of my reactants is Q. So this is correct. So 2 is correct. And so we can eliminate B. Let's look at point 3. A catalyst lowers both Q and R equally, therefore does not affect delta H. A catalyst does not interfere with the energy of the reactants or products. The catalyst only serves a singular purpose, which is to decrease the activation energy and increase the rate of the reaction. So if there was a use of a catalyst, the only thing that the catalyst would do would be to provide an alternate pathway by decreasing the activation energy. So the only option that is correct is option 2. So that means our answer is C. Question 1.2, consider the reaction presented or represented by the balanced chemical equation below using rhodium as a catalyst. Now you'll notice when you look at the reaction, rhodium is not there because rhodium is not part of the reaction even though it is a catalyst. It does not react with anything. So any closed system of carbon monoxide, nitrogen monoxide, and rhodium, which of the following graphs below best represents the change in the amount of rhodium over time? Now, a catalyst does not react in a reaction, and a catalyst does not get used up. So the amount of the catalyst remains constant during the reaction. So the answer is A. Question 1.3. Dihydrogen sulfide dissolves in water according to the following chemical equation. What is the effect of adding hydrochloric acid to a solution? So what happens if we add hydrochloric acid? The hydrochloric acid is not in the reaction, but we know that hydrochloric acid, HCl, dissociates into H plus and Cl minus. Now in solution, this H plus then becomes H3O plus. Now H3O plus is in our reaction. So adding HCl means that the amount of H3O plus will increase. Let's use Le Chatelier's principle to figure out what's going to happen. If you increase the amount of H3O plus, the system will want to decrease the amount of H3O plus. The reverse reaction is favored. And if the reverse reaction is favored, H2S will increase, H2O will increase, S2 will decrease, and H3O plus will decrease. The question is asking what happens to, what effect will this have? So option A, the concentration of sulfide ions increases. Will sulfide increase? No, sulfide will decrease. So A is out. Option B, the concentration of sulfide ion will decrease. You can see that the sulfide ion decreases, so our answer is B. Question 2 reads, the reaction of magnesium carbonate tablets with hydrochloric acid was used to investigate the effect of different factors on the rate of reactions. In each experiment, the mass of the tablet was the same and equal volumes of acid were used. Write a balanced chemical equation for the reaction between magnesium carbonate and hydrochloric acid. So magnesium carbonate is MgCO3, and that's reacting with hydrochloric acid, HCl, and that's going to produce MgCl2, so magnesium chloride, plus H2O plus CO2. Now it's not balanced. We can see that the amount of chlorines is not equal. So we'll put a 2 here, and that should balance it. Question 2.2, describe an appropriate experimental method to measure the rate of the reaction. So include appropriate measuring equipment. So what we can do is, if we look at CO2, we know that the CO2 that's going to be produced is a gas. So we can measure the rate by capturing the amount of gas, and we can capture it using a syringe. So we'll use a syringe and a stopwatch. Okay, and the syringe will then capture the volume of CO2 gas produced. And then you can record the volume and the time that it took to form. The results of the 5 experiments are tabulated below. Experiment 1 through to experiment 5. 2.3, can the results of experiment 2 and 4 be meaningfully compared? Answer yes or no, give a reason. So experiment 2 and experiment 4, let's highlight them. So 2 and 4. So they change the concentration, they change the temperature, and they change the state of division. So the answer, we can't compare them, because there's more than one independent variable. Remember, if you want to compare two things, then you need to have one independent variable so you know what's causing the change. So they could have changed the concentration but kept the temperature and the state of division the same. Or basically keep one column, change one column and keep the other columns the same. 2.4, what conclusion can be reached when experiment 4 is compared to experiment 5? So experiment 4 and experiment 5. Let's look at what's changed. So experiment 4, 2 moles per dm cubed concentration, 2 moles per dm cubed concentration. The initial temperature was 30 and here was 26. So the only thing they changed is the temperature. Both started at the same concentration. Both had a solid whole tablet. So the initial temperature was changed. 4 had a higher temperature, and you can see that the time for the reaction was lower. So the conclusion is, if you increase the temperature, the rate of the reaction increases. You can see that it has a lower time. A lower time means a faster rate. Question 2.5. Compare experiment 1 with experiment 2. Explain the results with reference to collision theory. So experiment 1 and experiment 2. 1 is here, 2 is here. Experiment 1, experiment 2, same concentration, same temperature, but different state of division. 1 used a whole tablet and 2 used a crushed tablet. So the change that we are observing has to do with the state of division. So the crushed tablet took a shorter time, so the rate increased. So using collision theory, why did this occur? So if you increase the state, or not state of division, if you increase the surface area, you have more particles that can collide, right? You're going to have more effective collisions per unit time. And if you have more effective collisions, you're going to increase the rate of the reaction. Question 2.6. The graph below shows the Maxwell Boltzmann distribution curve for the reaction mixture in experiment 1. The activation energy for the reaction EA is marked. So what is activation energy? It is the minimum energy required for a reaction to start. Okay, minimum energy for reaction to start. 2.6.2, what does the shaded area of the graph indicate? So they are asking about this area right here. So that represents the fraction of particles, or the amount of particles or molecules that have enough EK to react, right? So the area under this curve represents all the molecules, all the particles, and the shaded region represents just that small amount of particles or molecules that have enough energy for the reaction. Question 2.6.3, redraw the graph. Draw a new distribution curve for the reaction mixture in experiment 3. Label this curve experiment 3. So we need to compare 1 and 3. So 1 and 3. So the difference between 1 and 3 is that 1 had a lower concentration than 3. Now, when you are comparing Maxwell Boltzmann curves for concentration, the change in the change rather in the graph is only going to be with respect to the size of the graph. So a higher concentration, like in experiment 3, is simply going to make the graph larger. It's not going to shift it in any direction. So experiment 3 will literally just look like this. So it is just a larger graph because it has a higher concentration. The peak should stay in the same area, and because the graph is larger, what we'll then notice is that you're going to have a larger area here. And if you have a larger area there, then you're going to have more particles that have enough energy, and the rate would then increase. The rate of the reaction, that is. Question 3 reads, consider the equation below, which represents a hypothetical equilibrium reaction. Question 3.1, why is the temperature of 40 degrees Celsius specified? So they tell you here, Kc is this value at 40 degrees Celsius. And the reason is because Kc is temperature dependent. If the temperature is changing, then the Kc will also change. As a matter of fact, temperature is the only thing that affects Kc. Let's move on. Question 3.2, write the expression for the equilibrium constant of this reaction. So Kc is equal to the concentration of the products divided by the concentration of the reactants, and coefficients become exponents. So in this case, it's going to be the concentration of A3, B2, and there's an imaginary 1 here, so it's to the power of 1, divided by the concentration of B to the power of 2. We do not include A because A is a solid. So question 3.3, 0.3 moles of B was added to a 2dm cube reaction vessel containing some of A. The container was sealed and allowed to reach equilibrium at 40 degrees Celsius. At equilibrium, there were X moles of A3B2 in the container. Use the Kc expression to set up a mathematical equation that can be used to solve for X. It's not necessary to simplify or solve. Okay, so here we need to use a Rice table. So RICE. Now we're just going to focus on the compounds that will have a concentration. So I'm not going to include I'm not going to include A. So here I'm going to have B, and then I'm going to have A3B2. Now R in the Rice table stands for ratio. What is the ratio of these compounds? It's going to be 2 to 1. Initial, what is the initial amount of these compounds? So they tell us initially 0.3 moles of B. So 0.3 here. And in the vessel, the reaction hasn't started yet, so A3B2 will be 0. Then they tell us at equilibrium, there were X moles of A3B2. So at equilibrium, here is going to be X. Now the most important, arguably, row in this Rice table is going to be the change row. So how much did A3B2 change by? It started at 0 and it's now at X. How much did it change by? It changed by X, so plus X. Then to work out the change in B, we need to use the ratio. The ratio is 2 to 1. B to A3B2 is 2 to 1. So if A3B2 changed by X, B will change by 2x. But here we'll put minus 2x since it is a reactant and reactants decrease over time. Now at equilibrium, you're going to have 0.3 minus 2x. Now don't forget, this represents the number of moles. To get the concentration, we need to divide by the volume. Volume was 2. So 0.3 minus 2x divided by 2. And here is going to be x divided by 2. Now we have our Kc expression. We've written it in the previous question. So let's just write it again. So the Kc, it's still at 40 degrees, so the Kc is not going to change. So 1,65 is equal to, the concentration of A3B2 is x over 2 divided by the concentration of B is 0.3 minus 2x over 2. So 0.3 minus 2x over 2, and it's squared. And that's our expression. Question 3.3.2, simplifying and solving the mathematical equation gave two answers. So you have one value for x is 0.56 and the other is 0.04. Explain why the value of 0.56 is impossible if the container contained 0.3 moles of B. Okay, so let's just focus on this B right here. So remember, we started with 0.3. It changed by minus 2x. And if they tell us that x is 0.56, so 2 times 0.56, so 0.3 minus 2 into 0.56, that's equal to minus 0.82. We can't have minus 0.82 moles of B at equilibrium. So that doesn't make sense. So that's why it's not applicable. Because if we had 0.56 moles, then you would have a negative mole of B at equilibrium. And of course, that's not possible. Question B, calculate the equilibrium concentration of B in the reaction vessel. So obviously then it means we are using this value. Now if we want to solve for the concentration of B, we know the x value and we know the expression. The concentration of B was 0.3 minus 2x over 2. We know the x value, so 0.3 minus 2 into 0.04 divided by 2. So let's just put that in our calculator, 0.04, and then divided by 2, 0.11. So 0.11 moles per dm cubed. Okay, let's move on. Next question says, the reaction is repeated using a catalyst with all other conditions remaining the same. Write down only increase, decrease or remain the same. So what will happen to the value of Kc? So remember, the only thing affects Kc is temperature. So nothing will happen. It will remain the same. The value of delta H, a catalyst does not affect delta H. The only thing a catalyst does is that it will decrease the activation energy. So it will also remain the same. Let's look at 3.4.2. The graph of the original reaction rate time is given below. Redraw the graph in your answer book on the same set of axes. Draw the graph to show the effect of a catalyst from time t0. Okay, now this is a rate graph, and if we use a catalyst speeds up the reaction. So in other words, a catalyst increases the rate. So the new line for the rate will be above the current one. So what we need to do is we need to draw a line here. So our solid line and our dotted line will be somewhere here. Also, it will reach equilibrium. In other words, it will flatten before this time right here. So we just need to make sure that it flattens before that. Okay? And then we just need to draw our lines, our curves. So the rate is going to be higher at the beginning. So it's going to start at a higher point, like so. And then for the dotted one as well, it can't start below 0. So it's going to start at 0, but it's going to curve like this. So two things to look out for. It needs to be higher it is higher, and it needs to reach equilibrium or flatten out sooner. So this one flattens out roughly here. So just those two things to look out for. Question 3.5, the reaction rewritten below is carried out at a lower temperature. Okay, they want to know what happens to the yield. So if we decrease the temperature, now according to Le Chatelier's principle, that favors the exothermic reaction. Now if you look at the delta H here, that means it is an exothermic. So the forward reaction is favored. Forward is favored, right? And if the forward reaction is favored, it means that that's going to increase, that's going to decrease, and that's going to decrease. So what happens to the yield, meaning what's going to happen to the amount of products that we make? We're going to get more. Okay? What happens to the value of Kc? If A3B2 increases, remember Kc is the concentration of the products divided by the concentration of the reactants. If the amount of product is increasing, as we said in the previous question, the Kc will increase. Okay? And remember, the Kc will increase here because we are changing the temperature, right? So if, let's say, for example, they change something else and it resulted in a forward reaction being favored, but the change was not temperature, then the Kc will stay the same. The only reason we are saying that there's going to be a Kc change is because there is a temperature change. Okay, moving on, question 4. A sample of N2O4 gas is sealed in a container and heated. The N2O4 gas decomposes to NO2. They give us the reaction. The graph below shows how the concentrations change as a result of some changes made. Okay, so here's our graph. Fine. How does the rate of the forward reaction compare to the rate of the reverse reaction at the following times? So at T1 here, right? How does the rate compare? Now this is before equilibrium is reached. Remember, the first equilibrium is reached somewhere here. So before equilibrium is reached, the rate of the forward is going to be greater than the rate of the reverse. So it's going to be higher, right? At T2 now it's at equilibrium. And at equilibrium, we know that the rate of the forward is equal to the rate of the reverse. So they are equal. Moving on. At T3, some NO2 gas was added to the container. Redraw and complete the graph below. From T3 to T4, show the effect of this change on the rates of the forward and the reverse reaction. Okay. So at T3, they show us here that something increased. NO2 increased. So if they increased the amount of NO2, right, the first thing that we need to understand is that the rate is going to increase. Okay, so why is the rate increasing? Because we have more particles now. And if you have more particles, you have more effective collisions. And if you have more effective collisions, you have a higher rate. So the rate is going to increase. So it's going to be somewhere here, right? It doesn't really matter where, but it's going to be somewhere here. So your dotted line and your solid line will be here. But now we need to use Le Chatelier's principle to figure out what's favored and what's going to increase more, what's going to increase less. So if I increase the amount of NO2, the system will want to decrease the amount of NO2. It's going to favor the reverse reaction, right? And so that's going to increase and that's going to decrease. Now the reverse reaction is represented by this dotted line. So if the reverse reaction is favored, remember, the one that's favored will increase more. So dotted line will actually spike up like this, and then it will come down. Whereas the solid line is just going to curve to the new equilibrium. I just need to clear this up. And that's our answer. Moving on, question 4.3. Sharik incorrectly says that the change at T4 was an increase in the volume of the container. Okay. State, do not redraw the graph, how the graph of concentration versus time would differ if the volume of the container had been increased. Okay. So remember, this is a concentration graph, and concentration is equal to number of moles over volume. So if the volume had increased, as Sharik said, so concentration is number of moles over volume. If you increase the volume, there should be a sharp decrease in the concentration. So at T4, you should have seen a sharp decrease like this and a sharp decrease like this, then a change like so. Right? So the key word then is that there should have been a sharp decrease in the concentrations if the volume had increased. 4.3, the actual change made at T4 was an increase in the temperature. Okay, make use of Le Chatelier's principle to explain the observation. All right, so we go back to our reaction. They increase the temperature, okay. So if you increase the temp, right, so here's the answer. The system will favor the endothermic, right? The forward reaction is endo. And so the forward is favored. Now, we can see that if the forward is favored, the amount, let me clear this. If the forward is favored, the amount of NO2 will increase and the amount of N2O4 will decrease. You can see NO2 increasing here. You can see N2O4 decreasing there. And so that's our answer. Thanks for watching, everyone. Don't forget to like, share, subscribe, and I'll see you in the next video. Bye-bye.